brought to you by the Mathematical Association of Victoria and the Mathematics of Planet Earth, an international celebration and important message about the mathematics that we need to keep this planet safe and sustainable, brought to you by the Australian Mathematical Sciences Institute. The Mathematical Association is a body that is devoted to the valuing of mathematics in society, partly because mathematics is an extremely important science, but mostly because mathematics can be beautiful and can be found in all sorts of interesting places. Melbourne has been blessed by some great architecture. It's also been blessed by having some great mathematics communicators. You've read them in The Age, the Melbourne Maths Masters, that's what The Age calls them. Dr. Burkhard Polster and Dr. Marty Ross. And they've been writing for several years and presenting lectures for several years designed to bring the beauty of mathematics home to an audience of students, parents, interested maths geeks, and the rest of us. And today is a very special day because we're able to bring the Maths Masters to one of the most significant mathematical buildings in Melbourne, Federation Square. And today's presentation is given to you by Dr. Burkhard Polster from Monash University, and it's the Mathematics of Melbourne. Please welcome Burkhard Polster.
Thanks, Simon. Yeah, so welcome all. Where are you actually from? Which school is that? Oakley Grammar, so you're not too far away from Monash. So you probably all see you eventually at Monash. That's it. Okay. Now, I want to tell you a little bit about Melbourne and tell you a little bit about mathematics. First, a bit of an introduction. So I'm Burkhard. Over there, the crazy-looking guy is Marty. There's actually a third person in our team, which I also have to introduce you to. Can anybody read what it says there in the URL? How would you pronounce that? How would you pronounce that? Most people say it's quack cat, but it's actually not. Does anybody know what it might mean? It's not the quack cat. No, that's not the Kit Kat either. Alright, so it's the QED cat, right? So it's a QED cat, and QED is actually something that people used to say at the end of like complicated mathematical arguments. These days they call it like quite easily done, but which was called erodendum strandum in Latin, so it had to be proved. So that's our logo, the QED cat, and he's going to be a little bit of a guide today, the QED cat, alright? Okay, so it's going to be about Melbourne's mathematics that's kind of visible everywhere in buildings. And I've got a couple of pictures here of buildings that I'm not going to talk about. So, well, maybe just a little bit to get started. So, for example, the building on the left, you've all seen it? Can you tell me where it was taken from, the picture there? Where was it taken from? Where was it taken from? How can you tell? Ah, yes. So he's actually seen a reflection of a helicopter. I've asked this question before. I've actually got one really amazing answer to this question. And the answer was, well, maybe it was taken by a giant vampire with a helicopter-shaped camera. Anyway, could be. Now, another building down there is that strange corner in front of the State Library. So if you just head up Swanston Street, you come across this chopped off corner there. And there's actually some mathematics in there. So you've probably seen this before, 3, 4, 5 triangle. It's actually good for many things. Among others, you can impress your love interests with these sorts of things. So what you do is you do 3 plus 4 plus 5 is 12. And then what you do is you make a necklace like this, which has 12 equally spaced, very expensive diamonds, and you give this to your love interest, and they will be very impressed. But they will be even more impressed if you show them the maths that you can do with this. Right? So what you do is, you kind of go like this, 1, then you go 1, 2, 3, and you go 1, 2, 3, 4, and you go like this, and you've got a right angle here. All the time. So you just kind of carry this thing around with you, right? And it's all diamonds, so they're either impressed by the diamonds or they're impressed by the mathematics. Anyway, it's a really good present, so I recommend this. And it's hidden there in that curious corner. So they actually did something like this when they designed the curious corner. They had not a necklace, but a string like this with 12 knots. And they pinned like the 5-meter long segment to the floor. And then they had somebody kind of holding up the 3 and the 4 and kind of adjusted it there until it looked about right. And that's how this corner was actually constructed. But I'm not going to talk about this, so don't worry about it. All right. Now, you may not be familiar with this, but actually Melbourne is the city with the most mathematically inspired architecture in the whole wide world. And I actually only found out about this from an American guy a couple of years ago. So he wrote an article in 2006, Ed Peck, quite a famous guy, and he calls Melbourne the city of maths. And here's a couple of examples. So what do you think the buildings were in 2006 that he was kind of impressed by? So what kind of buildings in Melbourne, not the ones that I showed, but other ones, was he impressed by in 2006? Well, he's sitting in one. Okay, so there's one. There's a couple other ones. Let's have a look. When it comes to the best place on earth for eye-popping mathematical art on a huge scale, no place seems to compare with Melbourne. So that's foreigners saying it. And, well, I should be pretty proud of this. So this is the first example. Does anybody know where that is? Anybody know where that is? You know where that is? Can you yell it out? Yeah, that's the Storey Hall. So it looks like a skinned dinosaur. So if you look at the picture on the right, that's actually what you see when you head up Swanston Street. It's this scaly kind of facade. And it actually gets really, really impressive when you head inside. So that's kind of RMIT's hall when they have like big functions. They go inside and it's all surrounded by this mat. And I'm actually going to talk quite a bit about this one there. Then the next example I had was that building there. Does anybody know where that is? Has anybody seen this one before? It's right opposite Etihad Stadium in the Docklands. And actually Australian Customs is in there. And it's kind of, so it looks a bit weird. Right? It looks like it's all wonky. And if you kind of walk around in there, it seems like you're kind of constantly kind of falling over. It's a very nice effect. And then the third building he was impressed by was this one here, Federation Square. So three, and that qualifies Melbourne as the city of maths. We could actually talk about a lot of other buildings here in Melbourne. Double this, triple this, and make it even more impressive. But anyway, I'll probably go for those 3 buildings in the following, with a couple of other things thrown in. Okay, so just have a look at this one here, so what it does, okay? So this one is just kind of done from scratch in a drawing program, okay? So it really shows you what the facade does. So it seems to be all over the place. So I just want to show you what happens when I actually take out the color, when I take out the squares here, okay? So when I take out the squares, those lines actually become completely horizontal. Right? So it's just parallel lines. And when you put those squares back in, all of a sudden you see things going all over the place. Like this, like that. So the floors in this customs building are actually completely level. Right? So there's actually no problem walking around in there. It just appears to be a bit off. Now, I mean, to call this mathematical is actually a bit, I don't know, yeah, there's a bit of maths in there, but it's more like an optical illusion, really, right? Well, I mean, it's a kind of weird way of filling the plane with squares, so that's mathematical, but that's about it. So I'm actually not too impressed by the whole thing in terms of mathematics. Cat, are you impressed? Cat's impressed. All right, just phase it out again. Bring it back in. And that's actually where it comes from, right? So that somewhere in the UK there's a cafe, and some people just decided to tile the wall in a strange way, and all of a sudden somebody stepped back and said, well, this looks strange, right? So from then on it was called the cafe house illusion, right? So it's cafe house illusion. It actually got a cup. I've got it somewhere in my bag, I think. Somebody gave this to me. It's got the same sort of effect. You can kind of go around and it looks swampy all the way around. Okay, recently somebody came out with a book, and it's all about mathematical architecture, and about a quarter of what's in there is about Melbourne. And just to give another example to watch out for, next time you're at Healesville, there's a veterinary center, a wildlife center, and it's got this very, very strange roof that you can see there sticking out. So you can only, usually you go there for the kangaroos and the wombats and other things, but actually the mathematicians go there for that roof, because it's this other strange surface that you can see down there that you see in action there. So some architects thought this looks fun, so we'll put that strange surface on the wildlife center. So if you actually look at it from the bottom, that's what it looks like here. So it's kind of a triple symmetry. Okay, let's get going. So the first thing I want to tell you a little bit about is this building here, Storey Hall, right? And maybe you're heading up there later on. Don't know. Are you going to go up Swanston Street later on? Not today? Another day? All right. Anyway. So this building is very interesting. So I got really interested in it when somebody sent me an invitation to attend a function there. And what you see there on the right is actually the back of the invitation card. You can't see it there. I'm just going to highlight the text in a second. What's really good about the text is, for me anyway, was, what made me interested is, it seems to be like everything they say there is wrong, right? So it's an invitation, basically by the people who own the building who are really proud of it. At the same time, everything they say about it is wrong. So what I want to do is kind of use this as a little bit of a guide to figure out what's right about this building, okay? So this is exactly what it says. I'll just read it out for you, okay? So the dynamic tiles featured throughout the venue were inspired by renowned Oxford professor of mathematics, Penrose. Anybody know Penrose? No? He's really famous. Okay. The venue reflects his discovery that instead of 20,426 types of geometric shapes, required to cover a continuous surface in a non-periodic pattern, it could be done with just two, a rhombus of 54 degrees and another of 72. Well, that looks pretty impressive. Let's just have a look at what's true about this. Again, this is basically by RMIT. These are the people who are going to mark you down if you study there. And if you sit in this hall and you take your exams and you make a mistake, it's not going to be good for you. At the same time, the same people write this. Well, we'll have a look at what the rest says. So we're going for an easy target first. The business about the rhombus of 54 degrees and another of 72. So let's have a look at this. Okay, so here's a close-up of the wall, okay, and it shows you some of these rhombuses. Okay, so cat shows me the fat one, that's that one here, and that's the thin one. And we've got angles here. Well, we've got a really big one here that's definitely more than 90 degrees, and that's definitely more than 90 degrees. So what they must refer to is here, that must be 72, and that must be 54. Okay, so can that be true? Let's have a look here. So here we've got a thick one, a fat one, another fat one, another fat one, and two thin ones, okay? You can actually replace the two thin ones by a fat one, and it will just fit. So you've got four equal angles making 360 degrees. So 72, does this sound right? 72? If you take 5 times 72, do they make a full circle? 5 times 72, full circle? Yeah? Good. Okay, 72 is fine. Now, instead of the one that I just slide it in, you can actually put two thin ones, okay? You can put two thin ones. So let's just put the two thin ones back in again. Now they claim that the angle there and there is 54 degrees. Is that true? So what's the angle? 30, So what it really is 36 degrees, okay? 2 times 36 is 72. So it should be 36 degrees. Well, it might be a typo or something, so we shouldn't be too hard on that for this one, but still, it's a mistake, right? Okay, now let's have a look at this red statement. That's it's quite a bit of a mouthful, so let's go for it. So here they talk about tiling the plane in a periodic manner. You actually got all these sort of things happening at home. If you just go to the bathroom, chances are the walls are covered with square tiles. Have you got square tile bathrooms? You've got some? Yep, you've got some? Okay. And basically nothing exciting there. So if I give you a pile of tiles, and tell you to make up a square tiling, then you can do that. Right? I mean, anybody can do that. If you're in prep, you can do this. Okay, so it's not a big deal to make up these sorts of tilings, and I've got a couple of examples here. Right? I've got a couple of examples here. But this one here is basically bathroom tiling. This is a bit more complicated down here. I've got a tiling with kangaroos. Let's just go back. And, well, here's a sort of a statement, right? So he's discovered that instead of 20,426 tiles of geometric shapes required to cover a continuous surface in a non-periodic pattern, it could be done with just 2. Now, these are all periodic patterns, okay? All of them are periodic. What does periodic mean? Periodic means the kind of things repeat as you go in different directions, right? Like with the bathroom tiling, you just kind of go up, and you see the same thing happening all over the place. And if you go left and right, the same things repeat over and over again. Same sort of thing here, right? So with the kangaroos, if you go this way, there will be more and more kangaroos shifting back and forth. And actually, if you go up there, just the right distance, there will be another kangaroo just sitting exactly like this, but facing this direction. Oh, actually facing that direction. Okay, so somehow it's a big deal if you can tile a plane with tiles like bathroom tiles, and you don't get this repeating business happening. So somehow you need a lot of tiles, they say. Right? So like with the bathroom tiling, I just need one type of tile, and I can tile the whole plane in a periodic way that repeats. Right? Then the other ones, you've got this one kangaroo, tiles the whole plane periodically. Then we've also got some mixed types there with hexagons and squares and triangles. Not a big deal. 3 different types of tiles, periodic, right? But now you want to do it in a non-periodic way. Things are not supposed to repeat. And somehow this is a big deal, right? So how big a deal is it? Let's have a look. Okay, so here's an example. So this, instead of squares, just use rectangles again. Just use rectangles. Now that's a periodic tiling. Again, things kind of repeat as you go up, left, right. But can you change this in some way, in a very, very simple way, just kind of taking out a few things and kind of moving them around and change this into something that doesn't repeat? Can you do this? This doesn't repeat. And when I say it doesn't repeat, I've been kind of not very precise. I have to be a little bit more precise. Just imagine you've got this tiling there and it goes on forever, right? So we're really going on to infinity, right? Infinity. So an infinite plane filled with rectangles. And what I want you to imagine is that I make a photocopy of this on a transparency. Okay? So I've got the original tiling sitting there, and then a photocopy right on top of it. Okay? And I can bring this photocopy into coincidence with what I've got there in many, many, many different ways. Right? So I have the photocopy here, and I shift it up. Perfect coincidence, perfect coincidence. And I can go left and right and center, all kinds of different ways, and I bring it into coincidence in infinitely different ways. That means periodic. Okay? Now, can you change this pattern there? It's just a few different little moves to make it into something so that the transparency cannot be moved around. Can you, let's give you a hint, just 2 tiles. You just have to take 2 tiles and move them around a little bit, and all of a sudden, that pattern there, which is periodic, will turn into something that's not periodic. Can anybody see what you would do? Just take out 2 tiles, move them around. Yep, what do you do? Yeah, very good. What's your name? Elena. Okay, so you can sign up at lunch. So Elena has a good suggestion. What she suggests is we take out 2 of those rectangle tiles and just flip them like this. Okay, so let's just do this? So like that. And now just imagine, I've got my transparency, right? Now, in what way can I bring the transparency into coincidence with my pattern here? Basically, in exactly one way. The bits that are lying horizontal, the only way I can make them coincide with the bits that are horizontal in the transparency is by kind of putting them like this. Shifting them any other way will not form any coincident pattern. So this thing is not periodic. So something must be wrong with the statement there, because it's really, really easy to make a non-periodic pattern. You just need one type of tile. Not 20,426 tiles, different shapes, just one shape, a rectangle. With one rectangle you can make a non-periodic pattern. That's it. Easy. So something is very, very wrong with this red statement. So what did they actually mean to say? Okay, so let's just figure that one out. What did they mean to say? Well, first I'll show you a couple of other interesting ways of tiling your bathroom. Okay? So I mean, like everybody gets bored with the squares, at least I got bored with the squares a long time ago, and I've actually tiled my bathroom a completely different way. So here's a nice one. So what you do is you take a kind of a pizza and slice it like that, and then you can take the individual pizza slices and tile them with little triangles. And actually you can imagine this pizza kind of going forever, and you can tile the whole plate like this with just this one little kind of triangle that you see here. So you don't need anything else. And it looks like a wagon wheel, right? It goes out forever. That's a tiling with just one type of tile. Right? It's one type of tile, and it's got this rotational symmetry basically. Just one type of tile. And you can make this, you can kind of change this into something really, really crazy by just slicing it through the middle and shifting the two parts against each other. And then what you get is this guy here. And that's a nice one for a bathroom. So what you see here is actually, with this one kind of tile, you can create a tiling that has kind of these twists in it. Right? It kind of twists out forever. So just one kind of tile, you can make crazy, crazy things, right? Okay, so not a big deal. Definitely, the thing about all of these things are not periodic. Okay? There's the same kind of thing. Imagine the transparency hovering in front, move it around, out of coincidence. Right? So all of these things are non-periodic. Non-periodic. So, okay. So what's the big deal again? Well, there's one thing. If I take this little triangle there, I can actually make something periodic. Can you see, if you just take this little triangle, can you make something periodic out of that? I've got somebody to pick on now. Yeah, does anybody else know how you could take like a little triangle like this, just one triangle, any triangle really, and make it into a periodic pattern? I give you infinitely many of those things for free, and you just spend the rest of your life making a periodic pattern. Can anybody do this? Not that anybody wants to do it, I'll also give you a lot of money, identical notes. Alright, I'll just show you. So you can do it like this. Okay, so there's a pattern, okay? But that's periodic. That's periodic. Okay, now here's the idea. And there's something very mathematical. And actually it's also got to do with Federation Square. We're going to talk about this a little bit. At the time, like maybe 40 years ago, people knew a lot of different ways of tiling things in a periodic way. And they also knew a lot of ways of tiling in non-periodic ways. But what they figured out was that whenever you can tile in non-periodic ways, you can actually rearrange the tiles into something periodic. So any set of tiles that tiles in a non-periodic way can also always be rearranged in something that tiles periodically. Like this guy again, right? So you've got this one tile, tiles in a non-periodic way, but you can also use it to tile periodically. Anything else that we've seen, same thing, right? Whenever people discovered something that tiles in a non-periodic way, they could take the same thing to make up something periodic. So the question was whether they're actually tiles that tile non-periodically but cannot be arranged into something periodic. So that's the big deal. And the first example of such a thing, it's a monster basically, right? So it's a real monster. Consists of 20,426 different shapes. So there was 20,426 different shapes, and there was one way of taking many, many copies of this and tiling the whole plane in a non-periodic way, but no way you try, you can actually rearrange those things in a periodic pattern. It couldn't be done. That is pretty amazing. I mean, how do you come up with 20,000 tiles to do something like this? And anyway, Roger Penrose, the guy responsible for the scales on Storey Hall, he figured out to do this with just 2 tiles. So that was the big thing. But it wasn't actually just one step here. It wasn't just kind of going from 20,000 to 2. By the time he actually entered this story, they were kind of down to 6 already. Okay? So they had like 6 tiles that could tile non-periodically, but not periodically, and he brought it down to 2. And I'm just going to show you these tiles now. So here we go. These are his tiles. It's like jigsaw pieces, okay? So you've got a rhombus like this with a jigsaw indentation and extrusions, and you take infinitely many of them, and you can actually fill the whole plane seamlessly with infinitely many copies of these things. And whenever you do this, it's going to be non-periodic. There's just no way you can take these copies and actually make them into something periodic, actually pass through tiling. Okay? And it's pretty remarkable. Now these look a bit awful, actually not like the ones that you see on Storey Hall. So, I mean, the extrusions, what they do is, like this guy here, or actually you always have to look at the left ear of my cat, but that's where the pointer is. So this extrusion here, you can see it only fits in here and there. So it forces the tiles to go together in a certain way. It's called matching rules, okay? So these extrusions and indentations, they're called matching rules. They force the tiles to just fit together in a certain way. Now you can also do this in a slightly different fashion. You can color these things. So you color them like this, and take infinitely many copies. And now they fit together in certain ways so that colors fit together. I'll just show you what I mean by this. So let's just get rid of the cat. So there's the first piece, there's a second piece, and that fits. In what way does it fit? If you look here at the boundary, there's a white and then there's a blue. So they go together here, okay? You will take next piece, there again, white, blue fits. Next piece, next piece, next piece. Here is white, blue in action, but there's also black here, okay? So you can only fit them together like this, no other way. And this way, this is exactly how this Storey Hall is built. Okay, so here we've got 2 different sets of tiles, the ones that are used in Storey Hall, and the ones that Roger Penrose came up with. Can you see a difference there? What are the similarities? What are the differences? So this is Storey Hall, up here. This is Roger Penrose. What's the difference? Can anybody see a difference? What's the difference? Yeah. In one of the lines, the line doesn't connect. Right. Yeah. That's true, but it's actually just an artifact of the picture. So I was actually after something else this time. So what do you think? That's what I was fishing for, that's right. So in one of the tiles there's 3 different colors. So somebody else. Okay. So we've got somebody else lined up there. Alright, so this is Roger Penrose. Now again, what's the point of these tiles? What's the point? The point is, you can only tile the whole plane in a non-periodic way, okay? That's the whole point of the tiles. Otherwise, there's other options to go for. Now, the architects decide we can do better. We can do the whole thing with just 2 colors. We don't need 3 colors. We can do it with 2. Now, was that a good idea or not a good idea? But actually, it turns out it's not a good idea, because once you do this, the whole point of the tiles goes out of the window, and you can actually take tiles like the green ones and tile the whole plane periodically, no problem. I'll show you how. There you go. So, not such a great idea, right? So I have to mark them down for doing something pretty, well anyway. So, But still, it's weird. It's weird. When you actually look at the facade, it looks like it was done according to the rules. Right? So they didn't just, doesn't look like they just took the green tiles and put them right next to each other using the new matching rules. It looked like they actually used the Penrose tiles, put them together into some weird pattern, and then turned everything into green. So I can kind of live with that. So let's just see whether it actually works out. So here's the picture, and what I'll do is I'll just try to recreate the whole thing with the proper tile. So here, I'll start down here. That's this tile. It's the only way it can fit in. And now we'll just start going and just filling in how things are laid out in the actual building. And you can see it seems to all work out. Right? So it's all really, really good. So it's slowly building up there. All right. Okay. Not bad. There's something there. What's happened? So what's happened? What's happened? We've built this thing according to the rules. It's exactly what happens in the facade. Now we've got these two window-like things happening there. So we've got windows. Now in the windows, the only thing that can go in there is a fat rhombus. Can you actually put the fat rhombus in the window? What do you think? Can you put the fat rhombus in the window? Can you or not? Shake your head if you can't. Very good. Some shaking happening. Some turning around happening. Looking at somebody else. Okay. So you can actually not do it. I just put in the red window there. If I put it in like this, things go wrong on the left, right? So the matching rule are violated over here. If I put it in the other way, the matching rule is violated the other way. So it actually doesn't work. But still, I mean, what have we done? We've basically taken these Penrose things and we've just put them together according to the rules. You know, we didn't do anything wrong. We actually didn't do anything wrong. Still, we get to a place where it doesn't continue. And that's something very, very mysterious about these things. That, yes, it's possible to tile a whole plane with these tiles, but you don't have a chance in hell to actually do it. If I give you a pile of these things, and you just go and try to actually fill things according to the rules, you'll never, ever be able to fill the whole plane. You always come up with these inconsistencies there. It's something very strange. You have to actually know a lot of mathematics to be able to make up consistent patterns. Now, is this a problem with the facade? Not for me, because they actually adhere to the rules, and what these windows actually show is something mysterious about the tiles. That, you know, mere mortals can actually not come up with a good pattern. Okay, anyway, let's just keep on going here, okay? Let's just keep on going and complete the facade. So that's the whole thing. Looks all right, but let's have a close look at part of the building. And you tell me whether everything's okay here. Okay? Just have a really, really close look here and tell me whether you find anything that's not quite right. Do you find anything that's not quite right? Wait, we'll just direct the cat. The cat's going to help. Okay, cat up. Just kind of go like this or that. Down. Down, over. Other way. Bit to the right. That way. Opposite. Down. Bit more. Just a touch. Little more. All right, let's have a look. So what's happening around here? Yeah, it looks a bit discolored, but actually it still works. I mean, it looks like it's different colors here, but this part still does work. There is another piece of it though that doesn't work. Have another close look, have another close look. Up or down? Can't move it back, you can only move it up or down. Very well, move it. Up, 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 up. Right, right, right. Up. Right. So there's something that's definitely not quite right. There. So there's something really not right. Okay? There's something not right. It doesn't work. And right next to us, there's something else that doesn't work down here. So there's actually something really wrong about the facade. So next time you stand in front of it, have a look at the left side, right at the bottom here. So you kind of stand opposite, look at the left side. This is wrong, right? This is totally wrong. So that, I mean, you actually get this quite a lot, this architecture. There's architects who think that some sort of mathematics is a really good idea, and then they have their own ideas how they can make it better. And then usually they end up with something that's really not quite right. So I have actually some real issues with Storey Hall because of these mistakes, okay? Anyway, it's a nice facade. So now we've also got Roger Penrose here, and he was actually invited to the opening, and I don't know what he's looking at here, probably a mistake somewhere, but he was actually very polite. He was actually very polite. He actually didn't complain about anything. So that was nice of him. Now, I mean, why do you care about something like this? Why do you care about something like this? It seems like, you know, it's just some sort of thing that kind of mathematicians play with. Well, let me tell you, in 2011, somebody got a Nobel Prize for this stuff in chemistry. So what did he actually discover that got him the Nobel Prize? Well, what he did was he discovered these things in nature. So Roger Penrose kind of just played around with these things kind of in his mind and made them up out of nowhere. But then years later, somebody actually discovered these things in real life. So they found things that are called quasi-crystals that exhibit something that everybody thought was impossible. Remember when I showed you the first 5 tiles, just like a 5 pattern? Like a 5 rotational symmetry? That's what we found in the electron microscope. We found a 5-fold rotational symmetry in a crystal, and everybody knew that's not possible. There is, in traditional crystallography, you cannot have a 5-fold symmetry, like a 5-petal symmetry. It's just not there. And he found it, and he got a Nobel Prize for it. And I want to just show you where you can find like this sort of stuff in real Penrose patterns. So this is like a big catch taken from a Penrose tiling. If you actually squint your eyes, can you see lines in there? Can you see lines in there? Kind of really weird. I'll just show you some lines like this. So if you're a devil worshipper, you also love this kind of pattern. Anyway, so what they saw in the electron microscope was basically these stars, right? Which were in all kinds of other crystals that were known up to this point. You could actually not see these sort of patterns. So people got very, very excited enough to give this person Nobel Prize in chemistry. Now, what I'm a bit disappointed about is that Roger Penrose didn't get anything. Now, he actually discovered these things, like in mathematics. Somebody else discovered them in nature, big deal. And then immediately know what it was, because somebody had discovered them in mathematics before. So I think it would have been quite fair to give part of this Nobel Prize to Roger Penrose, but it didn't happen. All right, so that's all about Storey Hall, right? So I mean, just in case you wander up there at some point in time, right? I mean, something definitely to look out for is your little mistakes. And if you're really keen, can you just kind of stand there for an hour with a sign saying, "This is wrong, this is wrong." Something pointing there, "This is wrong. Fix it up." Right? It's a nice kind of school excursion. Okay, so what's the point again? Non-periodic tilings. Not hard, but non-periodic tilings that at the same time can't tile periodically, that's hard. And that's exactly what Roger Penrose did. Anyway, let's have a quick look at the Eureka building and tell you something mathematical about that. Okay, so this Eureka building is actually supposed to be, and the markings are supposed to be the markings on the surveyor stuff. And it all alludes to the gold fields. So that the golden top of Eureka Tower is actually supposed to be like the gold that people were digging for at the time. The red strip is some blood that was shed there. That was, what's it called? The Eureka stockade, I think. Yeah, so anyway, some people got killed, right? So blood was shed. And then the markings on the wall are supposed to be surveyor staff. I've got a real surveyor staff there on the right. Okay, so the architects take the surveyor staff and put it on the building. Now, can you just compare the surveyor staff with what's on the building and tell me whether it's the same thing? It's the same pattern? Is it the same pattern? It's supposed to be the same pattern. Okay, so what's the difference? What's the difference between the surveyor staff pattern and the pattern on the Eureka building? Yeah. So on the Eureka building, we've got one long line, then two short lines, long line, two short lines, long line, two short lines. On the real surveyor staff, it's different. We've got long line, two short lines, a longer line, a short line, a long line. Two short ones, a longer one. So why would you have a marking like this on the surveyor staff anyway? I mean, why would you divide like this in a weird way? Why would you do this on the surveyor staff? Well, the reason is because you're looking at these things from ages away, and you want to kind of figure out exactly where you are on the surveyor staff. Okay? So you want to do, I would say, like subdivision to 5. That's, you know, and you want to say, well, there's a subdivision to 5, and well, it's just above the long line, so it must be a 4, or it's just on the long line in between, so it's a 3, or just below, which is a 2 or 1. Another little puzzle there. You've got these markings there on the left, which is 1, 3, V, 7, and N. What do they mean? That's on the real surveyor stuff. What do they mean? 1, 3, V, 7, N. What do they mean? I don't think they use them anymore, but they used to. So there's a reason why you do this. There's some numbers, there's some letters there. Why are there numbers and letters? What do the letters mean? Okay, another free admission to Monash up for grabs. Okay, who can have any, so what can V mean apart from V? 5, correct. Alright, what can N mean? What could N possibly stand for here? So if this is 1, 3, 5, 7, what is N? It's 9, exactly. And why do you write 9 there and so N and V and not 5 and 9? Because they're easier to distinguish from the other numbers than, you know, if you did it the normal way around. So that's why they did it, right? It's just the markings, the way you do the markings and the way you label them is just there so you can actually look at this from far, far away and still kind of figure out where you are and stuff. Okay, so a bit of math there. Now, let's just have a look at Federation Square. So what do you think? You're here. This is a multi-million-dollar building. Is Federation Square correct or not? Or am I going to find a flaw? What do you think? Am I going to find a flaw? I am? Yeah, I'm a real meanie, you know. It's all I do. All right, let's have a look. Let's have a look. How correct is this one? Right? How correct is Federation Square? Okay, first thing I have to tell you is how you actually make up the title. Okay, so let's imagine during your next holidays, you're going for a vacation somewhere, and the plane crashes and you're stranded on a desert island. What you want to do is you want to recreate some part of Melbourne on this desert island. So what you decide to do is you go to recreate this facade that you just saw there from scratch. Can you do it? Well, after I tell you the secret of Federation Square, you can actually do that from scratch, forever now. Okay, now listen now. So what we need is a special kind of triangle, a right triangle. It's got short sides, and it's got a long side. The short sides are 1 unit long, and the other one is 2 units long. That makes it a very special right angle triangle. This trick doesn't work with any other right angle triangle, no other triangle for that matter. So you have to have that special kind of triangle. 1 unit, 2 units, then you get something amazing. Okay, now you take 4 more copies of this triangle and just put them together like this. Okay, now if you compare this triangle to the one that we started with, what can you tell me? If you compare the blue one to the red big one, how are they related? What's similar? What's different? Well, obviously, the one is bigger than the other. Somebody said something? Yes. Okay. Exactly. So the triangles are exactly the same shape. Okay? So how can you see this? Let's have the cat. If you look at this side here, that's 1. That 1 you get twice here. So that's 2, that's 1. This big triangle has exactly the same shape as the little triangle that you started with. And what that means is that you can repeat the trick. So you take 4 more copies of that big triangle and just nestle them around the red triangle and you get some bigger thing, super triangle. So that's kind of a super triangle. And now it is a super triangle, super triangle. And now we take 4 more copies of this and put this around what we have. And we get a bigger one and a bigger one. And if you just keep on going forever, you tile the whole plane. And this is how these walls there are made. Okay, and actually, if you want to really see this thing in action, you can look for the heart of every wall. Okay? So if you go out there and just look at a wall or take a picture of a wall, you can look for kind of a special triangle somewhere in there from which the whole thing can keep kind of built up. Right? So the heart would be a triangle. So you can have a heart here, and then you can find 4 more triangles around this one that make a super triangle. And you can take 4 of those super triangles to make a super triangle, and keep on going like this, and eventually fill the whole wall. And that will not work for any other triangle than this one special heart. Okay? So just go out there and try to find the heart. Okay, now the question is, we've got this big, huge tiling now, these triangles. Is this actually part of the ideal mathematical tiling? Can you find it somewhere in there? Okay, so when you look at a facade like this, is a big, huge rectangle. Now, the way it's built up is all about triangles. It doesn't say anything about rectangles. So are there actually any rectangles in what's called pinwheel tiling? So that's exactly it, right? It took me 3 hours to put this together. Time well spent, right? Okay, so that's the actual facade. Can you find this actual facade somewhere in the real tiling? Is it somewhere in there? Okay, let's have a look. Let's forget about that one. Okay, so that's the actual pinwheel tiling. That's the actual tiling, the ideal mathematical tiling. You can actually find rectangles in there. Just have a look. Can you see some rectangles in there? Yeah? It's kind of going all over the place, but you can actually see some triangles in there. Have a look. So there's all kinds of triangles in there. The question is there actually one big, huge rectangle in there that corresponds to a wall like out there, the one that I showed you? Okay, so how will you figure that out? How will you figure that out? Well, obviously I could draw a big tiling and it's going to look for it, but there's another really ingenious way, which you can actually do at home yourself. Just take a picture of some of these walls and then do this. Take any triangle in here, and then any triangle like this guy here, right? And then around this triangle you'll actually find a super triangle. And around every single one of the triangles in here, there's going to be just one super triangle. You can't do this in many ways, you can only do this in one way. Any single triangle in the pinwheel tiling is contained in exactly one super triangle. So what that means is, we should actually be able to kind of split this whole thing up into super triangles. Right? If it's sitting in the real pinwheel tiling, we should be able to split this thing up into super triangles. And I'll show you whether this works. So there's another one here. So that's the real facade. And yeah, it actually works. It actually works. So if you look at any triangle now, it's sitting inside a super triangle. So there's 5 of those little ones. So it's 5, 5, 5, 5, 5. the whole thing splits up into super triangles. So that looks really, really promising. But now, of course, every single one of the super triangles should be in a super triangle. And we can also check whether that works out. So let's just check whether that works out. So those are all the super triangles. Let's just see whether we can actually find the super triangles. There they are. So there's actually super triangles that kind of surround these sort of things. That's exactly what should happen if it fits into the real thing. And now how do we go on? So we've got super triangles, super triangles, and well, there should really be super triangles that split up this sort of thing. So let's have a look at this. Yeah, there's one. There's another one. There's another one. There's another one. There's another one. There's one. There's one sticking out, but that's fine. Now there's a bit of a problem here. So that shouldn't happen. Damn. We were close, you know, we were very close. But there's actually also something wrong with this facade. At a very kind of deep level, there's something wrong with this facade. I'm actually still quite happy with this facade. I mean, I'm a lot happier with this facade than the one on Swanston Street. Right? So, I mean, they actually tried hard. I actually don't know myself whether you could find a rectangle of that size inside the pinwheel tiling that could actually do the real thing. So, I mean, they did the best they could, I think. Now, there is actually some facades in Federation Square that do work. So I've highlighted one there. That actually works. And I'll just show you. So there's the facade on the left, on the right. That's the real thing. And I'll just show you where in the real thing you find this facade. There's once, and there's twice. So, you know, there's actually parts of Federation Square that work really, really well. It's just pretty much all the really big ones, they fall down at a very, you know, at the super triangle level. You find some mistakes. Have you seen this one here? This is actually not Federation Square. I just came across this in Singapore during a recent visit. This Federation Square copycat. Now, does this one work or not? Have a quick look. Have a quick look. Does this one work? She shakes her head. She knows me. Okay, now this one is actually really stupid. Okay, let's have a look. There's a square in there, right? So this is never ever going to work. Okay, so this one I'm definitely not happy with. Now there's another one here. I've got another copycat. Has anybody seen this one here? That's actually at Monash University. That's right next to my office. Does this one work? No, it doesn't. This is the worst ever. I won't even go into details here. But anyway, just to fix it up, this is the biggest building at Monash University, okay? This is what the Menzies building. If you're on the moon, you can see this building. Now, I've just got plans in with the Chancellor to fix this up into a major mathematical piece of architecture. So here's what I suggest we do. We extend this building like this and make it into the infinite Menzies building. It will be able to accommodate infinitely many people like myself, doing infinitely many things like what I just told you about, and hopefully some people will be impressed by this. Anyway, hope you enjoyed some of this, and just in case you want to be back next week, we're